Great. So this is our, actually, as we say, the sixth session of our AEC, Architecture, Engineering, and Contracting experience. Today we were going to focus on mechanical and electrical systems. We got to talking about it and somebody decided that plumbing is not real exciting. So we were going to focus on mechanical and electrical systems. And then it came up that we're going to talk about lighting in 2 sessions. So today we're just going to talk about mechanical systems. So we have 2 mechanical, I actually have 4 mechanical engineers with us today, 2 remote. So the 2 gentlemen that we have with us, we've got Tyler Johnson over there who flew in from Nashville, was also from Kansas City. So I'm excited for that, being a K-State guy myself. But he's been with the Henderson Engineers for 7 years. He does a lot of sports, recreation, and wellness design. He's actually the mechanical engineer for our indoor performance facility. And the word is he always goes the extra mile, which is good for a sports venue guy. We really appreciate it. He's done a great job on the indoor practice facility. He's going to give us kind of an overview of mechanical systems, what mechanical systems really do. And then we're going to turn it over to Brett Gilbert, who is here from Atlanta. He is our mechanical engineer for the Wellness Center. Going to talk about that facility. Carrie Parker is also online. She is our project architect. We'll loop her in a little bit more, and I think you've met her on some of the tours possibly. Then we have Timothy. I'm not going to try to pronounce your last name. Timothy Tirault, I think. Maybe I will.
There we go.
Anyway, he's a USF graduate. He's actually at TLC Engineering here in Tampa, but he's remote today. So we've got the local guys remote. We've got the remote guys in person. And then Matt Yin, who is our mechanical engineer, he focused on the smoke evacuation system that I know we talked about last week when we were touring the facility. So all those questions that you had when we were touring the building last week, bring them back up here because Matt will be ready to answer your questions. And Timothy has done a fantastic job integrating that in with the way out the Honors College building. So with that, I'm going to find our mouse and see if I can move forward here. Okay, maybe we need to go into presenter mode. Slideshow mode, maybe. Nope. Yeah, so we're not advancing the slides on the big screen. No, the clicker doesn't move things.
There you go.
Oh,
you didn't
back.
Want to point it at the right center.
All right, there we go. All right. So, again, ways to learn about the projects. Google AEC Experience. Join the design and construction team on Bulls Connect. As you guys know, this is an old picture because we've got the skin going up on the Honors College already. You've got a lot more steel going up over there, and you've got steel going up over there. It's actually looking like a building over there in the football area. So today we are talking about heating, ventilating, and air conditioning, otherwise known as mechanical systems. Talked about our speakers, and didn't change this, but you can talk about the indoor practice or performance facility, whatever you want to call it. So, turning it over to Tyler. Go ahead.
Awesome. Well, can you guys all hear me? I think you can all hear me in the room anyways. I don't know if anybody online can, so. Okay, perfect. All right, so my name is Tyler Johnson. I'm a project manager and mechanical engineer with Henderson Engineers. I was part of the design team responsible for the design efforts on the athletic indoor practice facility. You might hear me call it a couple different things throughout this presentation. It's athletics indoor performance facility, practice facility. It's all kind of interchangeable. So today, kind of what I'm going to talk about from the mechanical side is some of the decisions that we go through in our design process, mechanically speaking. So we're kind of start really high level, all the options and tools. Go ahead.
It's a performance facility.
There you go. We changed it on the fly. Perfected. So we'll kind of talk about really high level. We, as engineers, we have a lot of tools that we can use. How do we whittle it down, and how do we essentially make those decisions along the way? All right. Steve, how did you get it to go? Okay.
There you go.
Sorry, guys. Can you do it from the computer? There we go. Okay. I think we're working now. So just a brief overview for those of you who don't know a whole lot about the indoor performance facility. This new facility is going up in where the existing turf field location was along Sycamore Drive. It's essentially an 80,000 square feet indoor climate controlled practice field. There's a little bit of kind of support spaces along the south end there, as you can see. I'm going to try to use the laser pointer. A little bit of support spaces here, as well as a grand entrance lobby into the practice field area. And there's an observation deck along this corner that looks out over the practice field. It's primarily used for football performance, but it will be utilized for all student athletes as well as summer events such as camps, things of that nature, and donor events as well. So this two-story entrance lobby over on the southeast corner kind of turns into a multi-purpose space. So getting started, kind of going down the mechanical route, I know that not everybody here has a mechanical background, so I just want to kind of refresh everybody's memory and kind of go through the 101 here too. So the first law of thermodynamics, for those of you who do remember, is energy cannot be created or destroyed. So when we're talking about HVAC systems, a misconception is that they create cold air to condition a lot of these spaces, especially in warmer southern climates. But that's not really what we're doing. With HVAC systems, a primary goal of ours is just to move heat. So within climate controlled spaces, we move heat from indoors to outdoors. And even at times, we can move heat internally within the building from one space to the next space of the building. There we go. So at the beginning of the project, we have a couple of questions that come up is, what are we going to use for our cooling sources? So two good options are chilled water and direct expansion for HVAC systems. So the very first one is chilled water. We've got a campus there, as you can see. So as everybody's aware, the campus has its own chiller plant, actually several chiller plants. So one way that we can cool buildings down here is we can remove the heat within inside the buildings, reject it to chilled water, and push that back to the plant and let the plant essentially do the cooling at that location. We could also do on-site generation of chilled water. We could have our own complete standalone system that's not tied into the overall campus chiller plant. Or we could go a little different than chilled water is DX. So DX actually uses refrigerant as a medium for being able to reject heat. A lot of you guys are probably familiar with DX more so than chilled water in your house. You've probably seen a unit, whether it's in your attic or a crawl space, and that'll cool air within your house. And it'll reject heat through refrigeration back to what you've seen kind of sitting along either the exterior of your house, or maybe it's in your backyard, a condensing unit there. And that's where that'll reject heat that's taken from the inside and then pushed to the exterior. So when we're looking at these different cooling types, I think the other projects, specifically honors and wellness, make a lot of sense to tie into this chilled water. It's kind of a no-brainer, having been located so close to that southeast chiller plant where they're going to be cooled from. We don't have quite that much flexibility. We're a little bit further away from that southeast chiller plant. So the question about cost came up is, how much is it going to cost, and how intrusive, and how much is it going to get in the way of all these other facilities along the way? Would we be able to route back and tie into infrastructure in the near proximity? Does that infrastructure is it even sized to be able to handle the indoor practice field facility, or do you have to take it even further back? So we didn't quite have a really easy decision to make at the beginning of this project. So what we did with the university is we decided to complete an LCCA, short, an LCCA is short for life cycle cost analysis. And what essentially you're doing with an LCCA is you're evaluating the cost of a decision that you're making over a duration of time. So that's not just the initial cost of those systems. It's essentially the cost of them, all of these costs added up over time for a duration of time. And we specifically decided to go with 25 years. So an LCCA is a very collaborative effort between the design team, the construction team, as well as the university too. So all these parties get together and we come up with all the variables between different system types that could be utilized to end up coming to an end goal of which system type we are going to use in the end. So this is an actual LCCA that we did complete for the university on ours. So what we did at the top, you can kind of see the different schemes. I already kind of ran through a little bit of system type potentials at the beginning. So we evaluated scheme A, campus chilled water. So essentially extending the chilled water from the campus and utilizing that. We evaluated option B was on-site chilled water, as we mentioned, decoupling ourselves from the campus chilled water and having local generation on-site. We also looked at C, kind of similar to what we talked about for DX system, was with going with packaged air-cooled systems that would sit on the roof. And then D was an air-cooled chiller, also on-site, but not water-cooled. So within that, you can see the primary things that we're evaluating within this LCCA are the initial costs. And you'll see on here the initial costs are significantly different between the ones. That's because for anything that required you to do on-site generation, you've got to buy new chillers, something that you wouldn't have to do elsewhere if you're tying to the campus. However, the campus for this project specifically, because we were so far away, it was a considerable amount of cost to extend chilled water all the way over there. So that was a little bit prohibitive at the beginning, but after you came down to the end with replacement costs, service costs, the energy efficiency that you gain from utilizing chilled water systems, what we decided with the university is that even though after evaluating all those systems, what we wanted to do was extend chilled water from the campus. So that pretty much led us down the path of knowing how we are going to serve our building. From there, we knew that we were going with chilled water and it would be extended from the campus. So it came down to a question of what units are we going to utilize inside of the building for this. The two different units that we evaluated here were a traditional single zone variable air volume unit. I'm going to talk about that one first. So a single variable air volume unit is a unit that serves, like I'm stating here, very simple, a single zone. So it doesn't serve multiple zones. It is just dedicated to a single space. And with the IPF being set up as it is, with just a 100-yard football field, a single zone variable air volume unit is a great opportunity for that. This is just a rough sketch here of kind of what was evaluated initially. That unit could be ground mounted, or it could also be mounted up on the roof. But essentially what this would do is this unit would go through ductwork and be distributed throughout the facility, throughout the practice field. These systems are very great for even air distribution because with your ductwork, you can be very pointed in where you deliver your airflow throughout the space. But obviously it comes at a cost. Not only do you have pricing involved for the unit where it sits there in that location, but you also have the labor costs for that ductwork as it comes across. You have to pay for the man hours for people to go and install that too. So the second option that we evaluated here was an air rotation unit. So an air rotation unit is very similar to a single zone variable air volume unit in the sense that it's great for a single zone in that sense, but what it doesn't have is the additional ductwork with this. So these units are great for high volume and they function based off of rotating air. So their main purpose is to, within a large volume of space, is to push air and rotate that air continually and get enough turnover in that air so you have uniform temperature so you don't have any temperature gradients throughout. One challenge with these is that they don't have ductwork, so you can't have any interior partitions that would potentially block airflow from moving from one space to the next. But like I said, with it being one open space, that's not a challenge that was presented for us. Additionally, with these air rotation units, they're not mounted up on the roof, so you don't have any of the structural steel considerations. You don't have to worry about, increasing structural steel up at the roof, coordinating that with the engineer, the additional cost that might be presented there. They're pretty simple in their nature, is just standing alone on the side, and then they distribute out, throw it out high over the space, and then return it back low across the field. So this was the option that we essentially chose to go with because it was a very cost-effective solution for the indoor practice field. We ended up going with 2 separate units, one on the south side to kind of condition the south half, as well as one on the north side to condition the north half. So that is, I think, the end of the options that we kind of worked through in our design phase. So having said that, I'm going to open up for a quick Q&A. Does anybody have any questions about the process that we went through? Yeah, go ahead. That's a really good question. So he said, yeah. So his question was, with the air rotation, does that throw air only in one direction or does it throw in multiple directions? So that is a limitation of an air rotation unit. It only throws, let me wonder if I can go back and show this. Essentially, it's all sourced from this one location. If I can point here, on these louver bands, you have the ability to put fixed blades on these that could project it in different angles, but to a certain extent, you are limited in the amount that you can throw that in different directions. So it's all coming from a point source, and it can be angled out slightly, but you don't have as much flexibility as you would with a ducted system where you can actually duct it to individual spaces. Now, having said that, these are a great solution for a large volume space because you can throw it out and air will naturally due to stratification will sink down, and then you'll pull it back across the playing surface with return air. So you get a good sweeping effect. And the way that you combat that is making sure that you're returning over the air enough times and you have enough air changes within there. Great question. Yeah, so the question was, are you limited to 2 units or could you have multiple that essentially you could locate maybe even at 4, maybe each at the 20-yard line was the question. So you can do that. Yeah, you can put as many of these in as you want. Essentially what you're limited by is the cost, right? So you could put in as many as you want all around here. You could have one at each end zone, one at each sideline. What it's going to come down to is what are you gaining out of doing that, right? It comes at a cost to install that, piping, the unit itself, things of that nature. So multiple were discussed, and during our design process, we looked at, was it the best solution to put them here on the end zones, kind of centered there, or even put them staggered across the sideline? So that was another evaluation that we looked at. And the thought process that it came down to was that this was where our service entered the building. So being able to decrease our line size after this location would be the most cost savings for this project specifically, with only having to route a smaller line up to this side and not having larger piping runs all the way along the side up to here and having 2 units kind of centrally located on the sidelines. Any other questions?
So we show on the screen the benefits of an air rotation unit, and we talked about the limitations you have in distributing the airflow. What other drawbacks might there be with an an air rotation unit as opposed to other systems?
That's a good question. So another drawback is that you have to have a large volume of space, right? So air rotation units specifically are great for big volumes. If you start to divide the space multiple times, you're not going to get great service from an air rotation unit. So you're pretty much limited with these system types. You're limited to large warehouses, indoor practice fields, and things of that nature where there's nothing inside to get in the way of that air throw. Again, it's all of your source is right here at these ends, and there's no ductwork distributing down there. So that would be another limitation, why you wouldn't want to use an air rotation unit. It has a very specific practical use, and it's very limited in those practices. Yeah.
How did the team decide on 25 years to invest?
Yeah, so that was a university-driven requirement. So you can look at an LCC over a certain amount of time. You can do it over 5 years. You can do it over 15 years, 20, 25 years. A lot of that comes down to usable life cycle on equipment, right? So I think that was why the university chose to go with 25. with these different system types, I'm going to use an example here, package DX. So DX has compressors within it, and those compressors typically have a shorter lifespan than chilled water air handling units and chilled water components. So within the DX side, if you evaluate it at a really short period of time, that was going to be very cost effective to go with that route. But over time, as you had to continue to replace compressors and replace units, that cost would increase. So yeah, that's a really good point right there. Yeah. Yeah.
So this life cycle cost analysis is not just for mechanical units. We've done it for evaluating carpet as opposed to hard flooring, wood flooring as opposed to VCT. She's giving us the 2-minute sign. So you can take this philosophy of what is our initial cost, what does it cost to repair it, replace it, what's it cost to maintain it, what's its utility use for almost anything that you're doing, to really look at give yourself from a business standpoint, what is a long-term look at what you're actually doing, rather than just, okay, when I go to the store, it's going to cost me less to buy it than actually install it.
Yeah. I don't think that you have the LCCA in your part of the presentation, do you?
No, I don't.
Okay, so just to talk about that real quick, we use the LCCA on our design team to evaluate different system types holistically on what to serve the building. I think we mentioned earlier that it was a kind of a no-brainer for them to utilize chilled water from the wellness center, right? So an LCCA didn't make sense. It would kind of be a wasted effort to figure out if you're going with chilled water versus DX. So they used the opportunity to provide an LCC. And I'll let you.
Yeah, we did. Yeah, we can get into that a little bit too. We kind of build up to it, but don't let me forget to go back to that. Hi, everybody. I'm Brett Gilbert. I am the mechanical engineer of record on the Student Wellness Center, which I'm now going to go back to right there. I've got, I think on the line is Carrie Parker. Carrie Parker is my client on this project. She is the architect. Carrie, are you there?
I am. Can you hear me?
I think I hear a hello from Carrie. That's okay. Carrie
Looks like
has
it's muted
a
again.
formal speaking part here shortly.
Can you hear me now?
Yes, we can.
All right.
I've got my own echo, so put that back and we can open it back up to her this time. Okay, so let's get into the Student Wellness Center. Oh no. I should have known we were flying too close to the sun. There we go. Okay, so I'm going to give you a refresher on this. I think most people in this room, I think you have already seen something on the Student Wellness Center. But I'm going to catch you up. I'm going to refresh you, catch you up on it a little bit. So the Student Wellness Center is under construction now. It's just west of the Yingling Center. You're probably all familiar with that construction project. 47,000 square feet. It's a 3-story building. And it will house kind of everything you can think of from a student health function standpoint. It's got general medicine, everything from dermatology, behavioral health. There's an urgent care suite in this building, or will be. But what I'm going to focus on, because I'm a mechanical engineer, this is how I think about buildings, is that little bump on the top of the building there on the far left. And so we will get into what that is, but the reason we're going to zero in on it is that is where the heart of the ventilation system for this building resides. And that is most of what we're going to talk about in this portion. I'm going to zero in on the V in HVAC. So the V in HVAC is ventilation. So what is ventilation? Ventilation refers to moving air through a building, not recirculating it in the building, but moving it through the building. And you have 2 air streams that do that. There's outside air that just what it sounds like, brings outside air into the building, and then exhaust is the opposite of that. It takes air that's in the building and ejects it to outside. So my question for you is, why do this? right? So I think intuitively you probably understand that or realize that most of the time it's more energy efficient to recirculate air than it would be to move air through a building. So the question is why do that? And I'm sorry. So what I would ask you is, you know, in the world we're in today, like Earth things are top of mind. I think sustainability is one of those things, and I'm looking at about a half mast room right here. I think you'll agree the other is COVID. So what you have in front of you is these are CDC guidelines for some COVID prevention guidelines, and this on the left and on the right are from ASHRAE, which is the American Society of Heating, Refrigerating, and Air Conditioning Engineers. And if you kind of glance over that, you'll see a word that pops up quite a bit, and it is that word ventilation. Ventilation, demand control ventilation is in there. So outside air is there on the top left. So, you know, it is top of mind for the world right now, and it kind of always was. It's just that awareness of the benefits of ventilation are now heightened because of COVID. So that's definitely a trend, and that is definitely something that's going on in the world right now. So the question is, how did the pandemic affect how we designed Student Wellness Center? Just to put it in kind of time context, we began the design on this pretty much at the same time that COVID began. It was you know, think of the spring summer 2020 timeframe. Remember what was going through everybody's mind at the time? That's when we were making big decisions on this building. So, Carrie, this is a good time for you to chime in if you have architecturally some input you'd like here. I'll certainly talk about the exhaust and urgent care, but as far as COVID and architecture, do you have input there?
Yes, thank you. And I will speak a little slowly since it sounds like there may be an echo in the room. So
Yeah, you're okay.
all right, we actually started the design in earnest right at the beginning of the pandemic. So it gave us a really unique opportunity to work with the student health center and all the doctors to understand how their operations and methodologies have changed due to COVID and everything. And so we walked through a few options. We did already have in the program a few patient exam rooms that were to be like negative air pressure. So meaning if someone is suspected of being contagious in some way, they would go in there. So that way there is a reduced risk of them contaminating their environment. And this will segue into what Brett's going to talk about. What we decided ultimately was that the best thing would be for the whole urgent care department that is on the ground floor next to the ambulance drop-off. All of that from a mechanical standpoint would operate completely independently. So there is no air that gets that touches the urgent care that gets recirculated with the rest of the building. So if someone comes in really sick, like everything stays contained within there.
Yep, that is about the size of it. Good to go. We've turned you back off, Carrie. Thanks. Okay, sure. Yeah. The question is, where does the exhaust air go? Essentially, where is it ejected to? And so the answer is, so I'm gonna point to the diagram on the right. These are showing you the same thing in two different views, but the one on the left is that's the actual design drawing. That's a plan view of urgent care. All the yellow ductwork is exhaust ductwork. So that's showing you, as Carrie mentioned, all the rooms are exhausted rather than being returned. And on the right is, you call it an isometric view, but it's a 3D view of that same ductwork. So at the top of that, I should use the pointer. right there, that's a representation anyway. But that is the fan that is pulling all this air out, which you can't see is this is all the way at the top. So this is that penthouse we were talking about earlier at the very top of the building. This comes out of this duct comes out of the side of that, and then there's a fan that sits on the roof. So in answer to your question, it's exhausted. I'm sorry. Okay, all right. Well, it's exhausted at the roof level, but you keep a separation distance between exhaust and outside airs for that very reason. And 25 feet is in healthcare world is the minimum. I like to have them in separate zip codes. I don't want exhaust air and outside air anywhere near each other. Not in this, but so that essentially is it. So by the time anyone would breathe it in, it's long diluted into the the rest of the atmosphere. Let's keep going with this. So HVAC means energy. So I meant to ask this as a question, but I'll just show you. So if I were to ask you what the biggest energy consumer is in a building, what might you say? Well, the answer is in front of you, and it is HVAC. So notice that space heating and space cooling on this chart by themselves, that would be this one and this one, take up over 50%. This is the actual energy model from the building. This is real. This is how much annual energy this building is projected to use. And the other big chunk here is that's fans / interior ventilation. Ventilation's a bad word there. The terminology is not great, but that's just energy to move air. So whether it's ventilation air or not. So HVAC, by the time you look at all three of those pie pieces, is something like 3/4 of the energy in a building. That is how buildings work, especially a wellness center. You move a lot of air, and it takes a lot of energy. So the point here is that when you talk about ventilating a building for purposes of wellness, you have to be thinking about energy at the same time, because anything you do to the HVAC system, particularly that V in HVAC, matters a lot in terms of sustainability and the energy cost of the building. So yeah, one key point here is, all right, so you may say, all right, well, if ventilation helps, and it does, as we saw with CDC and ASHRAE, help us from an infection standpoint, why don't we just do more of it? Why don't we just ventilate buildings more? And you're kind of looking at the reason. The more you do it, the more energy you use, generally speaking. But there's more to it. So pathogens thrive in humid environments. The more humid it is, the more a pathogen wants to be in that environment. So you actually could, if you're not careful and thoughtful about how you design the mechanical system, you could actually be making things worse from a pandemic standpoint, not better, by adding ventilation. So the question becomes, what do we do? Like, how do we do this? How do we ventilate efficiently? Like, how can we ventilate without using so much energy? And what I would say is you have there's kind of two prongs, two approaches. It's to, I mean, essentially the reason ventilating costs energy is you have humidity in the air you've got to get out, especially here. This is different conversation in the northeast, northwest, but in Tampa, Florida, it's absolutely about humidity in the air. So it takes cooling and supercooling, ultra cooling a space to get the humidity out. I'm giving you a short version of something that's a lot more complicated than that, but dehumidifying energy is essentially cooling energy. So to do that efficiently, you either need to cool efficiently, you need to do the cooling process in an efficient way, or you need to do less of it. You need to have less demand on the cooling system. So that's really what we're talking about here. So back to what Tyler said earlier, this is the first of those two prongs. It's how you cool efficiently. How is the cooling process done efficiently? And here, and Tyler showed the data, our building is served from the chiller plant that's right there, right beside it. It's kind of a no-brainer to use the chill water that's coming out of that plant. It actually runs right underground right there. So we're tapping right into that chill water. And so not only is it kind of low-hanging fruit from a cost standpoint, this is an efficient plant, and Tyler showed that. So the point here is that using this plant as the ultimate cooling source for the wellness center is an efficient source of cooling. That's a major way, just by using the plant that's there, that's a major way that we can ventilate sustainably. Pardon me, well, I consult my notes. I went old school today. Yeah, so the other prong, so there's, as I said, there's to cool efficiently, there's also to cool less, just to do less of it. I'm going to use a car analogy. So, you know, if you think about your commute, think about the commute you might have made to campus today. So you think about the fuel you expend in that commute. There are kind of two ways to conserve that fuel, right? Way one is to drive an efficient car. Maybe you drive a hybrid, maybe you drive an EV, something like that. That's using campus chill water. Way two is to move closer to campus. It's to drive less. You can drive efficiently, you can drive less. So we're doing both. We're driving efficiently, and this is how we drive less. This is going back to that penthouse on the top of the building. We're going to talk about what an energy wheel, an energy recovery wheel is. So let's get inside that penthouse. So on the left, this again is two different views of the same thing, but on the left, you see this ERU. The pointer there, that stands for Energy Recovery Unit. This is it's something like Tyler's air rotation unit. I mean, it is a metal box with a fan in it, but the similarity is kind of in there. It's got two fans in it, one that pulls outside air through. That would be outside air comes in this side, it's the blue duct, goes through the unit, and then goes down into the building. Exhaust is the opposite. It comes out of the building, through the unit, and then back over the top of it, and then out to the point earlier about what happens to the exhaust air. There it goes. You notice it's not a coincidence that the outside air and the exhaust air are on opposite sides of the penthouse. That's on purpose. That's for that reason. So, and this shows that the same thing in three dimensions. But you see the energy recovery unit is this box right here, and then you've got ducts going in and out of it. The point is that the exhaust air and the outside air cross paths. They don't cross streams. The molecules don't get from one side to the other, but they touch in a sense. We'll talk specifically about what that means. So, and this is really where the magic happens. It's in this wheel right here. This is a cross section, so that what you're seeing is the wheel edge on. But there is a wheel that rotates in and out of the page between the exhaust and outside air streams. And the wheel is made of, it's kind of papery, kind of almost tissue papery. It is a media that is able to absorb heat, and significantly it's able to absorb moisture. So what that does is it takes the really nice exhaust air, from thermally speaking, exhaust air is awesome. It's cool and it's dry. It's the air in the building. And it allows the raw outside air to transfer its heat and moisture into the exhaust air stream, get ejected right back out of the building before it goes in. And that is the way that we efficiently heat and cool the building. And got the 1 minute warning, so let me blaze through. It does work. There's the actual data. This is again from the actual energy model. But notice we already talked about how important heating and cooling are. Notice the difference here. It saves some on heating. Gray is the baseline code minimum building. Yellow is our building in terms of annual energy use. But look at this energy savings in annual cooling. It's astronomical. I mean, it makes a giant difference. And it's how we're able to make this building holistically well. This is the main way you make a building, this particular building, a wellness center well in more ways than one. So it's thinking about you from an infection control standpoint, and it's also trying to do that in a sustainable way. So is there time for questions, or was that 1 minute warning it? Okay, cool. So we had one question earlier. How about others? Okay, hit me. That's right. Question. Yeah. The question is, we design for a target humidity level inside the building, and how do you plan for that? So yeah, it's a great question. So the answer is yes, and generally 50% is generally what we plan for. And I wish I had a good example to show you this. The answer lies in what's in the psychrometric chart, and in psychrometrics. Psychrometrics means air and water kind of mixed together. But the answer is for a given moisture level in a building, the colder the air, it's counterintuitive, the more the relative humidity. The warmer the air, the lower the relative humidity. So you have like two dimensions that you're trying to get into like an equilibrium, and you find a point. And generally 75 degrees, 72 degrees, and 50% relative humidity is about what's comfortable for people. That's about what this room is right now. And without going into all the details, I don't have the visual to show you now anyway to do it. The engineering fun part is that part. I mean, you do the calculations based on what that psychrometric chart tells you that how much raw cooling you need to get outside air down to the humidity level you need. The question is, do we only consider humidity as from the humidity source as the outside air, the ventilation air, or do we also consider ventilation sources from inside the building? The answer is both, but one dwarfs the other. The outside air is a source of humidity, especially in Tampa, Florida, is orders of magnitude more than any humidity source inside the building. People do give off moisture, especially if they are exercising and things like that. Sure, yeah.
If you have a high exercise space, those people are going to have a higher metabolic rate and they'll be giving off more latent load within those spaces. And that's what Brett's talking about here is latent load, which is essentially, as we all know, is humidity. So the more exercise you have going on, the more that then becomes in equilibrium to what Brett's saying with the outside air, which obviously still trumps, but.
Right. Yep, that's exactly right. Yeah. There are activities that do that. The wellness center doesn't have. In our particular case, and it's the case in most buildings, it's the case in this building. If you can take care of the outside air, you can pretty much take care of the humidity in the building, from a practical standpoint. Any other questions? Okay.
So we're going to turn it over to Timothy.
Do you want me to take control?
Yes, that'd be perfect.
Can you see my screen? All right. You see my screen okay, Steve?
We're trying to get your video working.
All right. You can flip it on your screen if it makes it easier.
Or did you just drag?
I don't know. Dragged it over there.
Did I lose you? Is anyone there?
I can hear you.
I don't know if the classroom can hear me.
No, I think they mute their speakers.
Yeah, so Timothy, we can hear you, but we just can't get you up on the big screen. We're working on that.
Okay. Do you want to take over as presenter and I can just follow along with the slides? That makes it easier. Can you give us some time?
Yeah, we'll do that until we figure out how to get you up there.
I have the same thing that you have on my screen if you want to pull it back up. Didn't mean to complicate things. I apologize for that. Scroll down 2 slides. Okay, so my name is Tim Theriot. I work at TLC Engineering. We were the mechanical engineers for this project. Matt Yin was the rational analysis smoke evac system engineer. that created the reports to help us decide what we were using in our system. So here's our beautiful building, the new Honors College. It's 5 stories with a 6th-floor mechanical room. It's open in the middle. On that bottom left picture kind of shows the cool artistic wood angled pieces that they used in there. Scroll to the next slide, please. If you can. So here is the equivalent of my penthouse in this Honors College building. This room has 2 big air handlers and a DAOS, which is dedicated outside air system, which is equivalent to what Brett was just saying was his energy recovery unit. This basically pulls in outside air on the bluish purplish duct. It brings it in from the outside and it delivers it straight into the units. So the outside air is delivered to the unit itself, the air handler 1 and air handler 2, through the return duct, which is in red. And then the unit with the yellow ducts there blows all that air down through a shaft and delivers out to the different floors. So this is not a single zone unit like we were discussing previously at the other center of the football field. This is a multi-zone unit. So there's quite a few zones. If I remember right, it's over 100 different zones that we have attached to these 2 units that are being fed outside air through that DOAS unit that's sitting there right there. So how does it do that? Does it just blow air in there? That's what we're going to look at next, I guess. You can scroll to the next slide real quick just to show you the components of these 2 units that we have. So that, please, for the next slide. While we're waiting for the next slide to show up. The green duct that was shown there is the exhaust system that goes through from below and through the DOAS unit, expels to the outside. On the next slide, I have a side view of the 2 units. We can go to slide number 29 there. So these units are providing a pressurized airstream through a massive amount of ductwork to get through 5 floors.
Timothy, if you want to take control, and we've got you up on the screen, you can wave to everybody.
All right, I'll try that again. Can you see me now? All right. I'm going to assume you can hear me and keep going if that's all right. So the other part of this dedicated outside air system is the green exhaust that we're showing. It comes up through the shaft right here from the toilets and whatnot, and comes through dedicated outside air system and blows out to the outside. We're also pulling air that would normally be returned for exhaust through the system to blow it to the outside. And as we've looked at in previous building, you know, this unit has a wheel right here that spins. So as this air goes through, this cold air goes through the wheel and spins it, it cools down this section of the wheel. The wheel spins up to the upper portion or lower portion in our case, and new outside air that comes in that's hot gets to effectively reuse that cooling and the enthalpy out of the air to cool down the air before it even makes it to the air handler. So that's what our system is doing. It takes the return air, exhaust air mix and blows through the unit through a fan to the outside, goes out. It brings in the outside air through here, hits the cooler part that's already been pre-cooled by this other air that went through as the wheel spins. Goes through some filters. My unit also has a heating and a cooling coil to help address outside air during winter and summer, and also to help with humidity. I have a UV light on my coil to help keep it clean, and the fan then blows it out. Now this is ducted to the back end of an air handler. This one unit goes to 2 air handlers, mixes with the return air, and it goes through the air handler, through filters, through some cooling coils, some UV lights blowing on the coil to keep it clean. And then from the fan, it is expelled out of the unit and down into our space through internal shafts. So it's going to go from the 6th floor down to, floors 5, 4, 3, 2, 1. And it'll have, a varying need for different pressures to be able to blow all that air down to the 1st floor, the 2nd floor, based on how it's used. If the floor is, say the 3rd floor is not used, the pressure will be less than it needs. So this fan itself needs to be modulated to speed up and slow down so that it can meet the actual needs of the building. If the building only needs half of its airflow, or if it needs 3/4 of its airflow, that fan will basically do that. And it does that through these, it basically senses that through the building automation system, and has a couple of variable frequency drives, one attached to each fan. So each of these fans will have that to be able to control and modulate on a multi-zone variable system. The variable frequency drive takes power from the power source, and it modulates the hertz on it to bring the fan rotation faster and slower. So it's basically taking the sine wave power, modulating down to this AC motor. To look at what I mean by pressurization in the building, remember those old videos where they poured liquid metal into ant piles? It's kind of what it looked like when they dug it up. It's a big wave of systems. Each one of these floors, all this ductwork is above the ceiling. So each one of these floors has its own duct system going through it. The yellow supply, the red's return. It looks like a big conglomeration spider web, right? So I went ahead and took that level down and isolated one floor. And this is just the supply on one floor. It comes down and it spreads out to the floor. There's a whole bunch of classrooms and tons of other rooms that want to control separately from each other. This guy wants to be different from that guy, wants to be different from that guy for each little classroom that's there. So how we do that, I brought it down one more level. This would go to one classroom. This is actually this piece right here, I believe I pulled out. So it's delivered through what's called a variable air volume box, or a variable terminal unit, it's also called. Delivers through this, being blown from the air handler, blown down, delivers through the box. The box modulates up and down. It has a damper inside of it that opens and closes, takes the higher pressure air from the air handler, and it makes it a little bit lower pressure, which you would normally get on a single zone system, and delivers through diffusers down to the space, down to the people that are below it. This box is connected to a thermostat. As you can see here, it's connected to a thermostat. That's on there. Sorry. Connected to a thermostat that's hanging on the wall. So the thermostat senses the environment in the room. Is it cold? Is it hot? Is it humid? And it sends that signal back to the building automation system. Building automation system will open and close these dampers at the box in the room to get more air or less air. So we'll have a higher pressure air here and a lower pressure air here. So this will just open up and close up to deliver the amount of air that it needs. It also senses how many boxes are open, how many boxes are partially open, how many are 3/4 open or half open or closed even, and it compiles all that together and senses it back to the air handlers so that it can read in the air handler how much to ramp up or slow down these fans. So the fans and the ducts themselves is not going to be able to handle like an infinite amount of pressure, but it'll modulate its pressure so that it can get the right amount of airflow into each room based on the needs of the person in the room, the people in the room. And that's pretty much building on what was said by Brett and Tyler, as far as what air handlers do and what energy recovery units do. See, also what we have in here, another system is what everyone's pretty interested in, the smoke evac system. So for my smoke evac system, you can see right up in here, there's a little blue interweaved into all this. That's the smoke evac system. I have 4 pretty big fans on the roof of this atrium next to the penthouse where the air handlers live. There's a supply fan in here. It blows down and it delivers some air down at the bottom right about here. It also delivers an air curtain of air on the 5th floor, which is around the perimeter of this atrium right here, just to kind of keep the smoke out, and the fans turn on. Now, we're delivering less air than we're exhausting, and the reason for that is once these big fans turn on, the windows open up, the doors open up, and other openings from outside brings in a large amount of outside air straight from the outside to come and deliver itself up and out the building through these big 4 giant smoky vac fans that we have. They have a fan that'll turn on that's separate from the air handler system, and that'll deliver the air down as well. So if I remember the numbers correctly, I think this delivers 80,000 CFM, and the 4 fans are exhausting 270,000 CFM. So it's getting the other 90 to 190, whatever CFM from the outside coming straight in. And it's a temporary situation, so we're not conditioning any of this air. It just goes straight out. The point of it is to get all the smoke out of the system, get all the smoke out of the building so you can see, so you can escape if there's an event or an emergency or whatever you need to. That's what this system does with these 4 fans. And they're able to pull all of that volume of air just out of the atrium, get it out of your way so you can get out of the building. This amount of air and the methods on where it was put in, the atrium air curtain that we have here, and the supply that gets blown down the bottom, even the amount of air coming in from the outside was all done through Matthew's rational analysis report calculations that he did to over the course of the design to figure out exactly how much we needed in this building. So the next couple of slides are his. Matthew, if you can hear, I can give this to you to talk about your slides.
Hi, Tim. Everyone, thank you for the explanation of the smoke control system. I think that's a pretty good illustration of the whole system. So what I'm talking about in the other few slides will be why we need a smoke control system, and then what is the components of that, and how we at what type of situation that we need smoke control system, and then how we gonna evaluate if the smoke control system is gonna be effective or not. And then as much of the system, HVAC system, that be regulated by mechanical code, but smoke control system is heavily regulated by the building code. If you look at the next slide, right, so this is basically the language from the building code. Let's say IBC, even though Florida, they adopted the Florida building code, but the language should be the same. That atrium that is 2 or more stories, in any building that has an opening more than have 2 or more stories, that is considered as atrium, but not all atrium need a smoke control system. Only the atrium that are connecting more than 2 stories, meaning that they have 3 stories or more, that will require a smoke control system to be designed in accordance with the building code section 909, which is the section regulates all the requirements regarding smoke control system. If we go to the next slide, this is basically the code requirements to say, okay, for the situation that you have the atrium, that the code said you needed to use exhaust method for the atrium as a smoke control system. And then the criteria that the smoke control system has been designed to is to maintain a tenable condition for occupant to evacuate. By saying that the section 909.8.1 said that the height of the lowest surface of the smoke layer shall be maintained not less than 6 feet above the working surface. So meaning that we need to maintain tenability condition 6 feet above the working surfaces. So that's the benchmark for our design. And going to the next slide, this is mainly talk about what components will be involved in the system. So first of all, definitely be the smoke exhaust fans, because that's the equipment that you exhaust the hot smoke and the gases during a fire. And then why you need a makeup, because when you exhaust the air out of the building is depressurized, but you don't want the building to be too depressurized. That's why you wanted to introduce air in to compensate the air being exhausted, so that you are achieving a dynamic balance condition in terms of pressure. And then that's why you need a makeup air. And then also you will need a smoke and fire detection system, because that's how the smoke control system being activated. Most of the time, smoke control system will be activated by smoke detectors. And depending on the location, they'll also be activated by the heat detectors. And then other than that, you also need a sprinkler system, because sprinkler system can also activate your smoke control system. Once that go off, you have water flow being detected, and then that will send a signal to the smoke control panel, and then to activate all the sequence of operations that are being programmed into the system. And the last component of the system is the firefighter smoke control panel. That's basically how that's more like a user interface for this smoke control system, especially when we test the system and during emergency, that firefighter can control the fans operation and then monitor the status of the equipment of the system. Going to the next slide. This is how Tim just mentioned that how we model the system. So we model system based on using the fire dynamics simulator. It's basically a program that to model a fluid dynamics of a fire-driven fluid flow and heat transfer models. So what we did is we grab the BIM model, actually the Revit model of 3D AutoCAD model from the architect, and then we import the model into our model, which is especially for fire engineering. And then we make some modifications based on that. And then we're gonna put in all the exhaust fans, supply fans, makeup air. We're gonna put a fire in it. Then we run the model through FDS. This is a screenshot. Then I think the fire in the middle of the atrium is burning at like 60 122 minutes. And that 2 minutes that you see that if you look at the lower level, that you have an opening already being opened up to introduce some airing. Yeah. And then so when we run this model, we need to see the end results, which is being measured through 3 different parameters. If we look at the next slide, we're looking at 3 different criteria. One, the temperature. Of course, temperature is important because if it is hot gas around you that is too high, you can't get through the spaces, that it's not tenable. And also visibility. The visibility is also very critical for almost every scenario, because once the smoke descending down to your vision line, that will impede you from finding a way out. And also, aside from visibility, you also have a carbon monoxide. So carbon monoxide is unique because that is a critical criteria, especially for small spaces, because in a small spaces that you will expect to get a very high concentration on the CO. Okay, going to the next slide. This basically showed that the visibility looks like on one of the floor, actually the top floor at the 20 minutes simulation. You got some failures at the corner, but that is not in that's actually within the opening of the atrium. It's not in our walking surface, which is fine. And going to the next slide. that is a design challenge. So we employ, as Tim just mentioned, that we have yes, there's a pink slot of a vent for blowing air. That is the air curtain to separate the smoke from the atrium. And going next slide, this is the visibility. This is the velocity of the air that coming through the openings that we need to maintain to be lower than 400 feet per minute. All the green is all the green meaning that the air coming, and the red is actually the hot gas and smoke. You see a little bit of turbulent at in the center of the building. So and then going further, entering the building, that'll be the the green. That is fresh air. So that's a smoke control system we design.
Thank you, Matt. Steve, do you have anything else? Any questions in the room you'd like us to go over? Looking here. I like looking at this one because of the spider web of ductwork.
Don't have any questions.
All right, awesome. Well, thank you guys for letting us show you our beautiful new addition to your campus. Anything else we can do, let me know. Thank you.
Thank you.
All right, thank you guys very much. It was interesting, especially seeing the smoke evacuation study. You can see really the purpose of that is to allow people to get out of the building safely. That's ultimately, you saw how they measured it. Can you see? Can you breathe? Can you get out of the building safely? And if you can, it's a success. If not, actually the predominant or the most people die in a fire, actually not from the fire itself, but from smoke inhalation. So that's why this smoke evacuation system in an atrium situation is really critical. And it's hopefully we never have to use it, but if it is, it's there and it is tested on an annual basis to make sure it is actually working properly. So any other questions? I know we hit some pretty in-depth stuff here today, but your eyes didn't glaze over too much, so that was it. That was a good thing. I think you got some good questions in there too. Anything else? All right. Thank you all very much. Thank you guys for coming in from out of town.